So time to talk about RSA, of course, the world famous RSA, the one that started it all, the first public key encryption. So we'll talk about the math and some of the problems, and then I have a culturally enlightened video you can see about some of the problems. So the math behind RSA, that's why one of the reasons I always loved it, the math is pretty easy to understand, much easier than, say, elliptic curves or discrete logarithms. So you just take the integers from 1 up to a prime number. That's the group. But each member, however, must have an inverse. So 0 is excluded. And so Z star 4 would only contain 1 and 3 because 2 has no inverse. But if n is a prime, then it does include all the numbers from 1 up to the prime minus 1. So these are really, Z star 5 contains 1, 2, 3, 4, and so on. So this is a nice, completely easy to understand group. This is a group of these objects. Now a group is a set of objects and then a transformation. And so here's the Z star 10 contains these, that's fine because you have no inverse. Then there's Euler's totient. So how many elements are in the group n? Now when n is not prime, but the product of several prime numbers, then this is pretty easy to understand. If I had only one prime number, there would be p minus 1 elements in the group. But if I have two prime numbers, then if I would like to if there's a product of two primes, then that means if this was, say, 5 times 7, I would have to remove every multiple of 5. I had all the numbers up to 35, but I remove all the ones divisible by 5, then I remove all the ones divisible by 7. So that's why you do this. Instead of the n is the product of p1 times p2 up to pm, and Euler's totient is where you take away 1 from each of these, because those will skip the ones you're not allowed to use. So the phi is the actual number of elements that are really in this group, which is less than n.
So then what is he multiplying? 4 times 6? 5
Yes, exactly. Yes, so if I have 35 here, then I would have 4 times 6, I can only use 24 of them. Only 24 of those numbers are actually in the group. That's exactly right. And for Z star 10, 10 is 2 times 5, so phi is 1 times 4. There's only 4 elements in Z star 10, because all the others have no inverse and are excluded. So now that you defined a group, so n is the modulus, the product of two primes, E is the public exponent, and it really can be almost any prime number. In fact, it can even be some numbers that are not prime, as long as they're relatively prime with n, but who cares? In practice, everybody uses the same number. This number is a common number. Some people use 3, some people use 5, and they've argued about it. As far as anybody can tell, it's all fine. And the main thing you do, though, is you choose a small value for E. And then the D will turn out being bigger. So the public key is n and E, and the private key is P and some other numbers you can get if you know P. So if X is the plain text message, you make the ciphertext by taking X to the E mod n. And the decryption, you take Y to the D mod n, where D is the decryption key. And you have to know P and Q to get the decryption key. That's why it's secure. People that know the encryption key cannot find the decryption key. That's the idea. Unless they could factor n into P and Q, and that's a hard problem. That's what makes it strong. So to calculate D, you have to have ED equals 1 mod phi. Remember, phi is the number of actual elements in the group. So this is going, if you take something to the E, and then you take it to the D, you're going to get back where you started. This is the inverse. So that's the point. So decryption is Y to the D mod n. That's X to the E, D mod n. That's X to the ED, that's X. That's the idea. That's why it's extremely simple and easy to understand. And I thought this was wonderful. There's a famous paper that came out in Scientific American in 1979 explaining this. And I read that and I thought it was the greatest thing ever. And so did a whole generation of computer scientists and people at that time. And so I tried programming it, but I had an 8-bit processor, and I tried putting it in, it was way too slow. I tried putting it in assembly code, and I had real problems making high accuracy mathematics in assembly code on an 8-bit processor to handle 100-digit numbers. And I gave up, and it's a good thing I did, because Phil Zimmerman is the guy that didn't give up. And he wrote the RSA code and put it on the internet and ended up in huge legal trouble with the US military for years. They tried to prosecute him. They said, you're leaking a military secret. What he didn't know and I didn't know, is the NSA figured this out 20 years earlier. Became in like the 50s or the 60s, the NSA figured out the RSA algorithm, and they used it for military communications. And it was a secret classified technique. And they loved it. It was great. Nobody could hack in. But then mathematicians on the outside reinvented it. Although who knows, maybe something leaks. But anyway, Diffie and Hellman had the essential part of it. And they published a paper, and that led to everyone knowing it. So then when people started writing software and distributing it over the internet, they regarded this as leaking a military secret, even though it had been public. And so he had huge arguments with the government for maybe a decade, and lawsuits and punishment and huge problems, because he made the software and distributed it. I wanted to do the same thing. I just wasn't smart enough to make it, which saved me a lot of problems. Anyway, and that's why mod phi, it's also called Fermat's little theorem. Any number to the phi is 1. Anyway, I'm not going to worry about this much. We'll use it later to find prime numbers is all. Anyway, so if n equals 10, that's 2 times 5. So that's a perfectly fine example of RSA, although of course it's too small to be secure, but it'll work here. So the phi is 4, like we said, 4 elements in the group. Now 3 is a generator of the group. If you take 3, here's 3 to the 1 is 3, 3 to the 2 is 9. 3 to the 3 is 27, so that will wrap around and turn into 7. 3 to the 4 is 81, that'll be 1. So, and then 3 times that is going to be 3 again. So you've generated all 4 elements. Those are the 4 elements in the group. So 3 is what they call a generator. And there are elements that are not generators, like if you start with 1 and raise it to powers, it's always just going to be 1. So you have to, there are generators, but not every element is a generator. So here's the powers of 3. 3 is a generator of the group, and the powers of 3 repeat with a cycle of 4. So now we encrypt by raising x to the e, and decrypt by raising y to the d. So we need to find d. So here's the public key. N is 10 and e is 3. Now the decryption key has to satisfy this. ed is 1 mod phi, and phi is 4. So I need to find the inverse of 3 mod 4. So I just start numbering. 3 times 1 mod 4 is 3. 3 times 2 mod 4 is 6. That's 4 plus 2. 3 times 3 is 9. That's 2 4s plus 1. So 3 is its own inverse. So if you raise something to the third power, you decrypt it by raising that to the third power again. That's what happens. And so you can try it. If the plain text message is 3, then I take 3 to the 3 to encrypt it. That gives me a 7. Then I take 7 to the 3, mod 10, and that gives me back to 3. So you can see it works for this simple example. That's how RSA works. And it's pretty easy to follow with small numbers, and it works fine with big numbers too. So we go a little bit up, we'll go to 14. 14 is 2 times 7. So there's going to be 6 elements in the group. So we have, we're going to start with 3. 3 to the 1, 3 to the 2 is 9, okay. 3 to the 3 is 27. So that's minus 1 mod 14 is 28 minus 1. That gets you to 13. 3 to the 4th is 81 mod 14. So that's a multiple of 14 plus 11. And 3 to the 5th is 243. And that'll get you another one of these. That'll get you another one. The point is, this is the generator. Here's the chart of all of them. These are the 6 elements in the group. All of them are generated, and you end up with 1. So that Z star 14 contains those 6 numbers. 3 is a generator. So now we can.
It's only the element that has it. It's only the element that has its own inverse that is the generator. And there can be more than one.
Well, no, they can have an inverse and not be a generator because 1 has an inverse, which is 1, and it's not a generator. So some elements are generators. I'm not quite sure what determines which elements are generators. Anyway, it's a good question. All right, so now we're going to find D. So I'm going to use an E of 5 this time, since I got a few more numbers to play with. So if E is 5, I just take, and I'm going to take it mod phi, and phi is 6. So I calculate 5 times 1, 5 times 2, mod 6, and I find that 5 times 5, mod 6 is 1, because 25 is 24 plus 1. So again, 5 is its own inverse. So E is 5 and D is 5. So if I take a message of 3 and take it to the 5th mod 14, I get 5. And to decrypt it, I take it again to the 5, mod 14, and that gets me back to 3. So that's what's going on here. And you just do that with bigger numbers, and that's RSA. So you got to generate those keys somehow. This is the hard part. We've already done a project where you try this, pick random primes, P and Q. That can be hard. You may have to try thousands of guesses to find prime numbers that are long enough. But it's not impossible. It can be done. Once you've found P and Q, then calculate phi, which is easy. Then pick E, usually just 6, 5, 5, 3, 7. And then calculate D, which is the inverse of E. Now, if you had to do it this way, it would be impossible. If you were going to just multiply and try to, this way, just multiply numbers trying to find the inverse. But it turns out there's an ancient algorithm, Euler invented an efficient algorithm to find the inverse for modular multiplication that finds it by a series of successive approximations, so it doesn't take forever. So, if you had a key that was 100 digits long, doing this would take 2 to the 100 calculations and be impossible. But Euler's technique takes much less.
He's using the triangle?
Yeah, you have some way of getting close and refining it step by step. So it takes only a small number of steps, like 50 or 100 steps, to find it, instead of taking an unthinkably large number. Yeah, so there is an efficient algorithm for it. All right, and so that's all you have to do. And you can do it with Python. After you have PyCryptoDome, you can import RSA, and we've done it before. We did it last time. You can create a key, and you'll see how long it takes to create the key, and it can get pretty a long time. We did it before, and we'll do it again later. So here's for speed of calculations, for example. If you have a length of 1024, which is not enough to be secure anymore, but we used those for a long time. So one key generation takes 0.15 seconds. 400 encryptions takes 0.02 seconds. And decryptions, 5 of them takes 0.11 second. Now this is because we chose E to be small, so encryption is really fast. D is much larger, so decryption is much slower, like 100 times slower. So your encryption is 1/400th of 0.02 seconds, so it's less than a millisecond. Decryption is 1/5 of this, so it's like 3 milliseconds. Much, much slower than encryption, and key generation is again much, much slower. That's the general pattern here. And so here I made a test where I tried different lengths. This is key generation. So 2048 takes 0.3 seconds, 4996 takes 1.3, 81, 114, 90, 1400 seconds out here. It gets really long. It varies a lot because it's just random. All the time is spent guessing prime numbers and rejecting them until you find prime numbers. And it has to take thousands of guesses to find the prime numbers. That's what's taking so long. And that's a matter of luck. So it gets to be a very slow process to generate keys. And this is why when we started talking about the risk of quantum computing, said it's going to crack RSA, one thought people had is maybe we could make the key longer. But the fact is you can't really make the key a lot longer and have it be practical. And also, it won't help. They say even if the key was 1,000,000 bits long, you could still crack it with a quantum computer. That's the problem. It doesn't slow down the quantum computer enough. So realistically, we have to quit using this system within the next 10 years or so. All of these I'm going to teach you, we have to quit using them. We have to use post-quantum systems, which we're just beginning to move to. So to encrypt with RSA, you typically use it with AES. Now, if you could use RSA alone, and that's what that original software from Phil Zimmerman did, the RSA software to encrypt your stuff. You could encrypt a whole email or a whole file or a whole hard disk just with RSA. The problem is it uses these really big keys that are like 2048 bits, and all the calculations are just really slow. It would really be a lot of CPU time. The fact is AES is much faster. So what you typically do is you just use RSA to encrypt an AES key and deliver it, and then you use AES, just to make it faster. Yeah.
Just as a curiosity, of course, the algorithm has to find prime numbers, so it has to compute, it has to test if the number picked is prime or not.
It has to guess a whole bunch of random numbers until one of them turns out to be prime.
How about I use I don't know how many prime numbers are known at this point.
Well, there's tons of them, but not 100 digits. The 100-digit ones, there'd be a list of 2 to the 100 approximately. And so they can't list them all, they can't find them all. That's the whole point.
And so in order to speed up the process,
Yeah.
the computational encryption,
Yeah.
would it help if I have a table, in the same way I have a table of IP addresses to allocate, and if I don't have the IP addresses you're looking for,
No.
redirects you
Well,
somewhere else.
a table of-
a table of prime numbers.
Well,
And
no.
select them randomly.
Well, see, if you did, then your attacker would use that table. I mean, if the table is not unthinkably huge, if the table contains 2 to the 100 elements, it's useless. You can't use it. You can't fit it in memory, you can't search through it. And if it contains a small number of elements, then the attacker can break in. That's the problem. That's why there are prime types, there are prime numbers that are easier to find. Like there's a whole bunch of them that are 2 to the n minus 1. So there are well-known big prime numbers, and you have to not use those because people know about those. You have to find one that nobody knows. That's why the current technique is you have to guess random numbers and then test them one by one to see if they're prime. That is the current, I don't know any way to fix that. Because the whole point is you have to make them so long that there are so many possibilities that nobody will ever find yours. That's right. Now, what you might be able to do, and we'll talk about that you do sometimes, is you use some tricks to make the calculation a little faster. That you can have like a mathematics table to save you some of the multiplication. That you can do. You can speed up the calculation by a factor of 2 or 4 by looking up things instead of recalculating them. That's as far as that goes that I'm aware of. So now this is what's called textbook RSA. You turn your plain text into ASCII bytes, put it in X, and then just calculate X to the E mod N. This is standard RSA. Now the problem is, it's got some weaknesses. For example, suppose you encrypt 2 messages, X1 and X2, with the same key. So you have X1 to the E mod N and X2 to the E mod N. Well now, if I just multiply the Y's together, I can so even though I don't have the key, I can construct a valid encrypted message by multiplying these together. Multiplying these together will be the correct encrypted version of multiplying X1 and X2 together. This is called existential forgery. I shouldn't be able to make any valid encrypted message without knowing the key, but I can. I can multiply together 2 ciphertexts and create a valid ciphertext, and that's a weakness of an encryption system. You don't want that. It should be that anybody, even if they look at all the ciphertext they want, they can't find the key and they can't forge anything that looks right. That's what you would like. So this is a weakness of textbook RSA. So in order to improve it, remember this is very much like electronic codebook mode for AES. If you just apply the encryption block by block, then you have the problem that identical input makes identical output. And that same thing's true here, by the way. If X1 equals X2, then Y1 equals Y2. So if you use this kind of encryption, you have the same problem as electronic codebook. You have repeating blocks of input will create repeating blocks of output. So both of those mean it's not really good enough for real use. This is the fundamental mathematical heart of it, but without adding more to it, it's not really going to do the job. So you have to add some kind of padding. And what you do, this is OAEP is what's usually used, optimal asymmetric encryption padding. Now, normally when you use RSA encryption, you encrypt something that is much smaller than the key. The key is something like 2048 bits, and usually what you're encrypting is a 128-bit AES key. So it's usually much smaller. You can encrypt large bodies of data with it, but it's not normally done. So what you do is you run the key through a padding algorithm, make a big block of padding, and then you run that through RSA to make ciphertext. And this includes extra data and randomness, so even if you have the same plain text come again, you'll get a different answer. That's typically how it goes. And so the algorithm for OAEP is in fact pretty confusing. The number of bits, here's integers fixed by the protocol. So the plain text message is here. Then you add enough zeros here. K1 is the number of zeros to add. Then G and H are random oracles like cryptographic hash functions, and you have an XOR operation here and here. And R is a randomly generated K0 bit string, so it's pretty complicated. We talked about these things before, far more complicated than the PKCS number 1 algorithm. You just pad it with zeros or ones or twos. But the idea is this takes your message, adds a bunch of random stuff to it, and gives you a long object to encrypt. And it's different every time. So this solves the problem. It's just pretty complicated to program.
Out of
Yeah.
curiosity, do you know the slanted line that crosses some links, the meaning?
No, I
Is a
don't really.
negative, is a negation of the operation?
No, I don't really know. I think it might be appending, but I'm not.
Appending?
I think it might be appending.
Okay.
You take this, you take, but I'm not really quite sure.
Okay, that's
Yeah,
fine.
I haven't programmed it either. Anyway, this is the standard one called OAEP. It's considered good. Like I say, the old method was PKCS number 1, volume 1.5, that was much less secure. This was the original RSA paper. The original RSA paper, remember I mentioned before, it said you should use 5 12-bit keys, which were considered secure in the 1970s when it was written. And they also had some kind of padding, very simple padding algorithm, which is what they recommended. And both of those have fallen out of favor. The short keys are no longer considered safe, of course, and this method of padding is also not considered safe. But of course, there is software that was written at that time that uses the older system. All right, so then you can sign that's encrypting with RSA for confidentiality. Then there's signing, which is another feature of RSA. You can sign a message, which is not intended to make it confidential, but just intended to prove the identity of the author. So what you do is you take X to the D mod N, and D is your decryption key, which is secret. So you treat the plain text message as if it was ciphertext and decrypt it. This will create gibberish, but the point is anybody can verify the signature by taking Y to the E mod N. What you encrypt with the decryption key can be decrypted with the encryption key, because D times E is 1. So if you can create something to attach to the message as a signature, and anybody can verify it by raising it to the E and observing that you get X again. And nobody could do that without knowledge of the decryption key. So this proves that you are the holder of the private key. That's what it does. So that's fine. And remember, signatures prevent forgeries, but they don't provide confidentiality. You could also encrypt it, but that's not the signature part. All right. And typically, if your message is long, you don't want to do this calculation for a long message, so what you do is hash it first, and then you sign the hash. That way you have a nice short object, just to save computing time. All right. So that's a textbook RSA signature. Now notice again, we have the same problem. If you just do X to the D mod N, then you can forge signatures. I could take 2 signatures and multiply them together and make a forged signature. Also for certain input messages like 0, 1, or n-1, this turns out to be, the raising it to a power doesn't do anything. 0 to a high power, 1 to a high power doesn't do anything. So there are certain messages, I could forge those, and I could forge signatures for them because the signature is something really simple, like 1 or 0. So that's why, again, the textbook signature is not really good enough. It has weaknesses. So there's also something called the blinding attack. So suppose you have a message which the targeted user would never willingly sign. You find a value so that R to the E mod N is a message they will sign. Then you get them to sign that, and you can calculate the signature for this message from it. This is like the other one we talked about. So if you can create another message where when they sign this message, you can figure out the signature for that other message. That's for these overly simple calculations. Simple connections between the input and the output make it possible to pull tricks like this. And that's all right.
When we say simplicity, we mean
if there's just one mathematical operation where you just take it to the E mod N, it's too likely that there are other things that will work. Whereas, if you have if like AES, you have a series of steps to make it so you can't easily reverse it and easily figure out how 2 of them can be combined, that sort of thing.
If I mix XORing and AND, it becomes more complex.
That's right. And that's the idea. When there's just one simple mathematical step, it's likely to have these unintended consequences where there are other ways to use it. So there's the probabilistic signature standard. This is the equivalent of OAEP. This combines the message with random and fixed bits to create the signature, and therefore you can't reproduce it without knowing the key. That's the idea. And then there's the simplest scheme is full domain hash signatures. You take the hash of the message and then Y to the E mod N. This, by the way, is perfectly fine because the hash function is the second step that you can't easily combine. Like if you have 2 messages and you multiply them together, that does not mean that the hashes are multiplied together. So just hashing it before running it through RSA is also a simple way to do it. This will prevent the blinding attack. All right, PSS came later. In principle, it is theoretically more secure, but in practice, they seem to work out about the same. PSS is safer against fault attacks, which are hardware attacks we talked about. All right, we'll get there. So in implementation, just of course use libraries. Never write your own code except as like a coding exercise. Don't trust any encryption code you write yourself. You should just use standard libraries. That's always the best move. So now, now another thing you could think about, if I have to calculate x to the e, and e is 1024 bits long, if I tried to do x times x times x, to the 1024 multiplications, I could never do that. So you don't do that. What you do is you use square and multiply. You calculate x squared, then you multiply those twice, you get x to the fourth, multiply those twice, you get x to the eighth. Now you only have to do a small number of calculations until you have all the numbers you need. You just one per bit. So it's the log of this is what you do.
I'm learning discrete math.
Yeah, this way you only have to do a reasonable number of calculations to make any exponent. And this is why I say there are tricks to make the math faster. Those work. Right. So that way you can do a 1024-bit exponent with only 1,536 multiplications, which, is possible, not that bad, whereas doing 2 to the 1024 calculations is utterly impossible. You could never do that. All right, it still takes a lot of CPU, though, because each one of those has to be done with 1024-bit integers. So you have long integers you're multiplying together, and you have to do 1,500 of those multiplications, but that's not too hard. And then there's side channel attacks. Now, the speed up from square and multiply means, if you think about it, you're going to combine some of these numbers. Well, wherever you're going to just write down the key in binary, and wherever you have a 1, you include that. Wherever you have a 0, you don't include that. So if the key only has like 4 ones, it'll calculate really fast and only do 4 of these. If the key has 500 ones, it'll take much longer. So the actual number of multiplications done tells me how many bits there are in the key. And that affects the time it takes. So if I just measure the time, I get a measure of how many ones there are in the key, and that's bad. That's information about the key that I shouldn't have. Also measuring power consumption or timing or radio emitted by the processor would all give you a clue whether it's doing a multiplication or skipping this one. That's the problem. So what you do is the best thing is to write a constant time library that never saves time. It goes and does the calculation for every one of these, even if it doesn't have to make sure it uses the same amount of cycles, the same amount of time, same amount of power, that sort of thing. So Evercrypt, as Microsoft made one of these. Evercrypt, they proved that it never leaks information in ways that can be exploited. So it's a different way to program, we talked about this before. Also, implementing stuff in hardware for AES is a solution. It always takes the same amount of time for every value of the key. So it's like a small e makes encryption fast, but decryption slow, and that's usually what people want, because typically decryption is being done on a server, like for your HTTPS connection, and the encryption is being done on the client, and your client is just a phone or something, so you want to make it use less CPU on the phone. All right, so the Chinese remainder theorem is something that makes RSA calculation 4 times faster. It's a little complicated, but there's a way to you had this operation x to the e mod n, and you can, since n is p times q, you can turn that into 2 smaller operations, 1 mod p and 1 mod q. And each one of those are smaller, so it's much faster. So this is called the Chinese remainder theorem, and it is just a way of making the math run through faster by exploiting the fact that n is not prime and can be expressed as p times q, so you can break that problem of x to the e mod n into 2 smaller problems using p and q. All right, and things can go wrong. There's a thing called the Bellecore attack, the fault injection. This is one I saw. If your CPU makes a mistake during the calculation, that has a non-random effect on the output. The first version of this I saw came out about 15 years ago. A guy took a processor and he lowered the power supply voltage to where the processor would start making errors. Then they ran RSA encryptions with, I think, a 1024-bit key, and they ran until 100 of them were wrong. And from the 100 wrong numbers, he's able to deduce the entire key, because he knew the algorithm and said, if you just drop 1 bit at one point, what will that do? And the answer depends on the key. So each one that was an error gives you information about the key. And it only took about 100 bad ones to get enough information to completely determine the key. And this is a problem because all hardware has flaws. In fact, even if your hardware is very good, there are cosmic rays that come down and knock electrons off silicon and cause bits. Every computer does drop bits sometimes. So in principle, this is a problem, and that's why they like the schemes that have randomness in them. That makes it so that the effect of flipping a bit is more random and harder to exploit. So, that's one weakness. And I'll mention a few more. Let's do the Kahoot first, and then I'll play the cultural video that will show you some more flaws. So here's a Kahoot. Oh, I got to log in. Yeah.
So the Chinese reminder theory is used only for encryption?
I think it has a lot of applications. But yeah, I think also decryption. I think for the same, by the same token, the decryption would be faster.
And what's the same? There's no really change.
I think so, because it really is based on n. The fact it's breaking on using the small numbers p and q instead of n, just to make it faster.
You reverse the operations.
Yeah, you do the operations 1/2 at a time, and that makes them smaller and faster. That's the basic idea. 10. I should have 10 somewhere. All right, let's try sorting. Well, I don't seem to have the option to sort. I used to. Something seems a little off. Oh, well, that's because I'm not in the right place. That's what's going on. Okay. There we go. Now, there we are. Now I found it. Good. All right. Good. Only got 6 people online. We may not get any more competitors today. There's only 6 live, and usually less than half of them come to play. So we'll carry on regardless. All right, so how many elements are in Z star 15? It's 8 because this is 3 times 5, so you take 2 times 4. It's p minus 1 times q minus 1. So the answer is 8. All right? And I see somebody, third person did join, so that's good. Anyway, all right. So what's Euler's totient for 35? There you go, 24, good. That's it, 35 is 5 times 7, so you take 4 times 6 for 24. And that's how many there are in the group, how many numbers there are to use for encryption. All right, so how do you save time on the client side? Yep. Low E makes encryption fast. Low D would make decryption fast. Low P would make it insecure. You need P to be big and long. And high phi, N is big anyway. You can't do anything about that. So anyway, it's low E is what makes encryption fast. That's what almost everybody always does. All right. All right, what's the slowest operation? Generating the key is what takes forever because you have to guess thousands of guesses to find the prime numbers. This is by far the slowest. Then decryption is the next slowest. Encryption and signing are pretty fast. But key generation is hundreds of times slower because there's no way out of just trying thousands of guesses to find the prime numbers. All right, anyway.